Okay, so we have all our equations. We need to try to figure out how to fix this problem. Okay, so the first thing, I'll just review very rapidly what we did yesterday. So we have a heat of combustion, and the heat of combustion, you know, we have different gases. One of the things that we normally do in fire is that we can group the materials in 3 groups. So gases like hydrogen will have a very high heat of combustion, you know, per kilogram of the fuel. Then everything that doesn't char, okay, more or less has between 45 and 50. So you can have propane, gasoline, paraffin, kerosene, polyethylene, you know, they all more or less are around the 45, 50 value, okay? And the third group is the charring materials, which generally are around 15. And then you have coal, wood, peat, PVC, and so forth. Now, again, there's no precision in this analysis, but it gives you a sense that the variability of the heat of combustion is not extraordinary when we're dealing with problems of fire. And given the precision of what we're doing, generally grouping them in 15, 45, and 140 is pretty much good enough. Okay? So then I basically explained that the heat release rate is the heat of combustion times the burning rate. And the burning rate, I can break it, you know, into the area that is burning times the burning rate per unit area. And that basically allows me to separate the area from the burning rate. Okay? So then I explained that I can transform the area into a circle that is burning from the middle and expanding for design purposes. Okay? And calculate that as a function of the flame spread velocity multiplied by the time. That gives me the radius. If I substitute this in here, I get the area as being pi Vs squared times T squared. Okay? So if I then substitute the area into this equation, I get this term here, and I'm going to lump all this as a material property and call it alpha, and this will be my alpha T squared fire. This is a very simple way of representing a design fire. Okay? This is why I'm going to input in here. Okay? So people have classified this, and depending on what materials are burning, you can create a little table that tells you I can group my materials in ultra-fast, fast, medium, and slow-growing fires. So if you have a room that is full of upholstered furniture, that probably will be more or less deemed as a medium fire, and it will have an alpha that is somewhere in between 0.0469 and 0.0117. Okay? So your fire will be somewhere in here, and you'll pick up something in between. Okay? Yes?
Guys, why would we just kind of go with a very conservative alpha?
Oh, you could. You could. So that's the engineering decision. So basically what you have here is people have done a whole bunch of tests, you know, measured these values and come up with a range. Okay, that is deemed as a medium fire. Now, why do they put a range? Because effectively, once you have a medium fire, for example, you will design a sprinkler system for a medium fire. You will design a smoke detection system for a medium fire. And that system is applicable to anything that falls within this range. Now, for your purposes of calculating egress, which is what we're doing here, and knowing what the smoke layer descent is, yes, I will probably go with a conservative value and use the bigger number, the 0.0117. Is that okay? Because that will descend the smoke layer faster, and that will be the conservative calculation of the time to flash over. Is that okay? So, but that's the way we will use this data from an engineering perspective. Okay? So then I have all this, and I know my fire, and then I go back, you know, to this concept of conservation of mass. Okay? So this is where the first trick happens. There's a tank. Okay? So this is a very common way of actually modeling fires. Okay? So effectively you can reproduce with a salt a density gradient that is comparable to the density gradient that you will get in a fire. So what I'm going to be doing there is I'm going to inject 10 cubic centimeters of salt water, which happens to be black. So the salt that we put is an ink, and effectively I'm going to make it heavier, okay, than the water. So the plume is going to be formed, and eventually it's going to hit the ceiling, and it's going to produce a smoke layer. Is that okay? Now, once I have the smoke layer, I can measure the volume of the smoke layer. So the 10 centimeters, cubic centimeters that I introduce in here. Now, keep in mind, I'm talking in volumes. Obviously, I have to multiply it by the density, but the density difference is actually not that significant. This is just for representation, okay? So I'm going to put 10 cubic centimeters in here. I'm going to let the plume entrain water. And what lands in here is going to be the smoke, no? So MS will be the volume of the smoke. MF will be the fuel that I'm injecting. Is that okay? And the difference between the two of them is the air entrained. In this case, the water entrained. Is that clear? Why am I doing this? Because I want to get a sense of which one is bigger. All happy? So let's do the experiment. So there's my 10 cc's that are being injected. There's a plume that gets formed, and then it hits the floor and it starts filling the smoke layer. Let's wait until it stabilizes. So my MF is 10 cubic centimeters. Okay? That's more or less stable. So the tank is 100 centimeters in length, 50 centimeters in width. Okay? So my area will be 100 times 50, no? Is that okay? So it will be 100 times 50, and my height, I have my little ruler here, measuring tape, is about 5 centimeters. Is that okay? So 5 times 50 is 250, times 10, 2050, times 100, 2500. Are we all happy with that? $25,000 cubic centimeters. That's my MS. So therefore, what is my MA? 24,990. Which one is bigger? Can I neglect the amount of fuel? When I'm doing conservation of mass and I have MA plus MF equals MS, is that okay? Everybody's happy? So if you look at it and I do the calculations, my MF divided by MA is 4 times 10 to the minus 4. Okay? So would be an acceptable error of 0.001%? I think so, no? Is that okay? Yeah.
Yeah. So what? I'm sorry. I don't really understand what's happened here. So we have.
Are you meant to understand what just happened?
So what's happening is like we're like reproducing this effect of like the smoke diluting with the ambient air.
Exactly. So the smoke, when it comes down in a plume, it entrains air.
Yeah. Okay.
So in this case, your heavy salt is entraining water, but it entrains it in such quantities, okay, that effectively what you have is literally air.
Right.
in all the earlier stages of the fire, you have very, very little products of combustion. It's mostly air being entrained.
It's heavily diluted.
It's heavily diluted, exactly. Okay? Yes?
Sorry, is it the density difference between your salt
And the water.
and the water, and that density difference is like the same order of magnitude of density difference between the smoke?
No, it basically is the same Grashof number.
Yeah.
Okay, so I do a scaling analysis, and so it's a relationship of viscosity and buoyancy. So I change the density so that I maintain a certain set of non-dimensional parameters. Okay, which is fundamentally the Fruit number, the Rayleigh number, and the Grashof number, mostly a Grashof number. Okay, but because the water has a very different density, viscosity than the air, then I can play with the density gradient so that I maintain the non-dimensional parameters. Is that okay? So that's very well known. It's called saltwater modeling, and people do smoke analysis by using the same thing. So you can put the model of a building inside the tank, and you inject a little bit of ink, and then you see how the smoke propagates and how it fills up the building. Okay? Is that all okay? So are you all happy with me ignoring MF? Is that okay? Which effectively gives me a set of equations, okay, and a set of unknowns that are appropriate, no? So now I can solve the equations, okay? Now there's one step that actually we still need to do. So once we neglect MA, then all these equations, MS becomes MA, and then that's it, okay? So in principle, now the system can be solved, okay? In practice, I still need to do another trick, okay? And the reason why I need to do another trick is because MA is very complicated. And MA is going to actually change with the height. So it's not that I have another unknown, it's just that I have no means to calculate MA. Okay, and I have to find another way of doing it, and this is normally what we tend to do, which is go back and look into experiments. Okay, so effectively what I'm going to do is I have all my equations, I know I can solve them, okay, but MA is so complicated in nature that I'm going to look at it on the side, and effectively I am going to calculate MA independently by means of a set of experiments, and then input it. So once I have MA, I know this, okay, and that gives me TS, and once I have TS, then I can go to these equations and solve the rest of the problem. Is that clear? So you were all so fussed about my use of the specific heat. Can I use a constant now?
Because everything's air.
Yeah, so everything is air, and actually it's almost at ambient because it's so diluted that the temperatures are very low. So my choice of using CP all over the place has been proven correct. Is that okay? No more fussing around with CP? Okay. So there you go. So basically now I can rewrite the equation and get the temperature of the smoke as being the ambient temperature, Q, which is alpha T squared divided by MA divided by CP. Okay? So how do I develop the entrainment? And this is extremely common in fire. Is the moment you hit a wall, instead of banging your head against the wall, you find the door. Okay? And so the person who devised this was an individual called Gunnar Heskestad. You know, he used to work at FM Global. And basically, they couldn't figure out a way to estimate appropriately how much air would be entrained in the event of a fire. So they decided to perform an experiment. And I would like you to tell me, how would you run an experiment to determine the amount of air entrained? And I'm giving you plenty of hints in there, and of course you have the notes in there, so you in principle should be able to tell me, but the logic is what is important. So how would you devise an experiment that will enable you to establish how much air is being entrained? So let's start by thinking first. What do you think are the variables that affect how much air is being entrained?
Fire diameter and height.
Okay, so when you say the fire diameter, can I actually substitute that, given that the heat of combustion is probably 45? Okay, can I substitute that just simply by saying the heat release rate? Okay, so if I can just say the air entrainment is going to depend on the heat release rate. In other words, the bigger your heat release rate, the bigger your air entrainment. Everybody comfortable with that? Yep. What else? That's it? Well, yeah, I see ambient temperature. We'll run all our experiments at the same temperature. Okay, air-conditioned room.
Buoyancy.
Huh?
Buoyancy.
The height at which
Yeah, of course. I mean, buoyancy is the one that creates it. So you have the invariance. Okay, so your invariance is going to be gravity. There's no question about it. We're not running this experiment in Mars, nor at the tip of the Mount Everest. Although some researchers actually do that. But anyway, so gravity is an invariant. The ambient temperature is an invariant. CP is an invariant. Okay?
Is it the size of the opening?
height.
Okay. Height, size of the opening. What are we talking about here? What is the height? What height are you talking about? The height, the free height of the smoke layer, no? Is the area through which the entrainment can happen. Is that okay? The smaller that number is, the smaller your entrainment. The bigger that number is, the bigger your entrainment. Are we happy with that? Yeah? All comfortable? Heat release rate, height. What do you call the opening?
Like
Huh?
like a valve. Like a valve, it just operates like a valve, so
So you mean the opening at the top?
no, from the side.
Oh yeah, well, that will be then the height, so it's the area through which it comes in. Okay. Anything else?
Exhaust rate.
Yeah, so the exhaust rate is what I'm going to use to be able to conduct my experiment. Okay? So I'm going to have a system by which I have a smoke hood. I'm going to fix the fire, and I'm going to put a burner here, and that burner is going to fix the value of the heat release rate. Is that okay? So as soon as I start burning something, I start producing smoke, and the smoke layer starts descending unless I extract. Is that okay? So this will be the M out, and if you are in training, this will be your M in. Are we happy? So what condition needs to be satisfied so that the height of the smoke layer doesn't change? Huh?
M in equals M out.
M in has to be equal to M out. Are we happy with that? So if M in is equal to M out, then H will not change. Okay? So how am I going to run my experiment? I'm going to put my hood, I'm going to send one of you to the corner to look at the dial, and you're going to go more. Oops, yeah, it's not moving anymore. Okay, stops. Okay, so what am I going to record? I'm going to record the heat release rate. Okay, I am going to record the height, and I'm going to record the M out. Is that okay? Why are you laughing? Is it funny?
No, but because I had some students in that extraction hood doing those experiments.
Yes, I know, I built it.
Because more like that, I keep getting experiments, you know, with doing things without thinking about what you're
Yeah.
So that's why I'm laughing right now.
Okay, good. So anyway, glad to be of entertainment. And so anyway, so that's how you run your experiment. So effectively, what am I going to do? I'm going to say, okay, fair enough. For each Q, I'm going to do a plot, and I'm going to do M out. Okay? And here, I'm going to put H. Is that okay? So if I do the experiment, I got one data point. Is that okay? So then next experiment, what am I going to do? Once I got it once, I'm going to tell the student and say, now increase the extraction. So the moment they increase the extraction, what is going to happen with the smoke layer? It's going to go up until it stops again, no? Because as it goes up, your M in increases, and therefore eventually they balance each other again, and then you get a new H. Is that okay? So then I get another point. Then I'm going to tell him do it again, and again, and now go down. Here's my plot. That is what is called an empirical correlation. Okay? Next, I'm going to say, okay, well, let's repeat the game, but now use a bigger heat release rate. So change the burner, put a bigger burner. Okay? And you start burning with a bigger heat release rate. Now, the same point that originally was here, now because it's a bigger heat release rate, it's going to have a bigger entrainment, so it's going to be here. Is that okay? And then I'm going to repeat the whole thing. Okay? And then I'm going to do it again. So Q goes up. Okay? H goes up, and that's it. I have my empirical correlation. So now I have a plot that actually tells me how much air I'm entraining as a function of H and as a function of Q. Is that okay? Now, of course, you know, we like to complicate our lives. And that plot doesn't necessarily present itself in an elegant fashion. So how do we make it elegant? Exactly. So we have to non-dimensionalize it. So how do we non-dimensionalize it? Yeah. Why would be the height of the flame? I mean, think about it. Yes, but you see, the flame is related to the heat release rate. But how is it related to the variable I'm interested in? The variable I'm interested in is the mass of air entrained. Is that okay? Do you follow what I'm saying? So the flame height is not necessarily physically related to this term. So in principle, I wouldn't try to scale anything as a function of the flame height. Okay, I have to find something else. So what is entrainment in itself?
It's the free jet dragging and mixing with the surrounding air.
So it's bringing the air in, okay? So if I do a cylinder of height h, okay, and I know what the radial velocity is, could I do area h 2 pi r times u times the density equals 2ma?
Where u is an average velocity.
Of course.
Okay. what is the radius that you're, does that?
The radius of the fire.
Okay.
Fire is not cylindrical.
Hmm?
Fire is not cylindrical.
I cannot hear.
Fire is not a cylindrical shape. It's
No, no, no. The fire is not cylindrical shape, but the air is entering through a cylinder towards the fire. Just simplifying it. Could do a cone if you want, but then it will be 1/3. No, no, but I mean, would this number here that I just created, in general terms, represent the amount of air that is entering that cylinder?
You've defined a control volume for your problem. You've defined a control volume for your problem.
Yes.
Yeah.
And all that area that comes, all that air that comes in there is going to go out in here. So this MA is going to be equal to this M out. So it's the same. No? It comes in through the cylinder, it gets out. Are we all happy with that? Nobody's upset at me? Okay. So let me now define the radius. Okay? So the radius, effectively, 2 pi r, pi r squared is the area times the heat of combustion times some burning rate is going to be equal to the heat release rate. So the radius is actually related to the heat release rate, okay, by a constant, okay, but to the square root, no? So r is actually the square root of q, or proportional. Okay? Believe me, we're just scaling. Are we comfortable with that? Yes? So how would I define the velocity? Yes?
Driven by the buoyancy.
By buoyancy, yes. So how do I create that?
Square root
Hmm?
of delta rho GH?
Yes, so basically if I do Bernoulli, okay, effectively you're going to say that this is going to be beta G T hot minus T cold times rho 0. No? Are you familiar with that expression? That comes out from Bernoulli. 1/2 rho u squared is equal to rho g. Is that okay?
And beta is your expansion coefficient.
My expansion coefficient, okay? So it will be, 1 over rho infinity.
So it's
Is that okay?
1 over rho infinity?
No, I
T
did
infinity.
1 over t infinity. Yeah, sorry, 1 over t infinity. Is that okay? Okay? So effectively, I can say that u is going to be proportional to g to the 1/2, okay? To the density to the 1/2, and to T hot minus T cold to the 1/2. Are we happy with that? So how do I express this temperature difference as a function of the heat release rate? Is that okay? If I subtract T hot minus T cold, I get Q over MA, which is the area, the value that I'm looking for, times the specific heat. Why are you looking at me like this? I mean, no, is that clear? So effectively, this term here is nothing but Q over MA times the specific heat. Is that clear? So at the end, I can say that U, okay, is G to the 1/2, rho infinity to the 1/2, Q over to the 1/2 over ma to the 1/2. Now then I substitute the ma back by this, so it gives me another u that comes in here. Is that okay? Constant, 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 constant. So it is u to the 1/2, no? So I can get rid of this ma, this ma, and turn it into u to the 1/2. Okay? I multiply it to the other side, and I get u. 1/2 plus 1 is 3/2. Is that okay? So effectively, I'm going to get u to the 3/2 is proportional to g to the 1/2 to rho infinity to the 1/2 and to q to the 1/2. Everybody happy? Yes?
Actually, I'm not because I can't see.
Oh, sorry, let me turn the light on. This problem with technology, you want us to use this and this? Okay, so basically I did u, g to the 1/2, rho to the 1/2, q to the 1/2. Is that okay? M to the 1/2. So then I substituted this by this, and I got another u which I multiplied to the other side. Okay? So I got u to the 3/2 is equal to this, this, this. So then I basically take the 2/3 power, all the halves go away, and I get that u is basically proportional to g to the 1g rho q all to the 1/3 power. Is that okay? Happy? So,
Which is the same form as your free convection law for laminar flow.
of course,
Okay.
because I'm doing the same thing. No? I'm not introducing turbulence at all. So effectively what you get is all these terms end up to the 1/3. Now, I made a mistake here. What was the mistake that I made? I made a mathematical mistake. I forgot one term. Huh? No. Get rid of CPs. No, 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 no. When I substituted, I forgot the h. Okay? So basically, I put u to the 1/2. I should have put u to the 1/2, h to the 1/2. Okay? So now I'm going to leave it there because you can finish the analysis if you want. All I wanted to identify is the fact that g comes to the 1/3, rho comes to the 1/3, and q comes to the 1/3. So if I want to scale the flow rate, I'm going to scale it by g to the 1/3, rho to the 1/3, q to the 1/3. Okay? And if I substitute all the h's the same way, this is why I noticed I had made a mistake, because the h here appears here, and then the h is going to appear again. So you have to multiply the h here when you get the total mass, and it comes to the 1/5. Anyway, you can do all the math and it comes out cleanly. But the one that I want that is really important is that, as you can see, the flow velocity that is proportional to the ma can be scaled by g to the 1/3, rho to the 1/3, q to the 1/3. Is that okay? So if I was to scale the velocities by those terms, then all this data will collapse. Is that okay? And I could do the same thing for h, but because of that 1/2 that I missed, instead of coming to the 1/3, it comes out to the 5/2. Okay? So I will have to scale by h to the 5/2, and then if I scale this by h to the 5/2, then everything collapses, not only down, but here again. Is that okay? So if I go to the equation in itself, yeah.
So you made the assumption when we use basically the Bernoulli's equation to set our velocity equal to the buoyant.
Yes.
The buoyant flow. So I guess I'm supposing that when we start getting to experiments or something that where turbulence is governing the problem, then we're going to start to see deviations from when we try to collapse these, not the equation or the results on each other.
Well, if this was a perfectly simple laminar problem that worked with Bernoulli perfectly well with no problem at all, then the moment that I scale everything, it will give me 1 because I got the perfect answer. Is that okay? But because I'm only scaling, it's not going to give me 1. Once I collapse everything, it might give me 0.2.
Well, and that's why you said it's proportional.
Yeah, that's why I'm saying everything is proportional, nothing is equal. Is that okay? So effectively, I'm just simply scaling down. And the only point I wanted to make is that once I do all the simple mathematics, effectively everything comes out to the power 1/3. Okay, and if I repeat the same analysis, but now I use the h, okay, the h will come to the power 5/2. Is that okay? So basically your mass of air entrained is proportional to q to the 1/3 and h to the 5/2, okay? So if I scale it down, then all the data collapses into a constant number. Okay, and that number happens to be 0.2. Is that okay? So if you look at it, then effectively, for every heat release rate, they accumulate the smoke layer. You have M in equals M out, and you get a height. Okay, that's the experiment, and you collect the data, and this is what you get for the data. This is the height, this is the entrainment, and this is effectively all the data for different values of the heat release rate. Exactly what I did here. Is that okay? So then, if I scale it correctly, then I can take all this, and basically, as you can see here, you get G rho to the 1/3, Q to the 1/3, and H comes out to the 5/3. Okay? And obviously, I got rid of the CP and the ambient temperature, but of course they're going to come in anyway if you do it correctly. Is that okay? So effectively, if you do it all correctly, what I wanted to show you was that the gravity, the heat release rate, they come to the 1/3 power. Okay? And that's the empirical correlation. So you know that they're proportional to that, and the constant of proportionality comes out as 0.2. Okay? Because obviously I'm only scaling, so the number is not correct. Is that okay? So effectively, what you're doing is doing a problem by which I can create the appropriate scaling laws, and I can reproduce all the scaling parameters, and they all come out the way they're supposed to come out, and then eventually all the coefficients, all the power laws and everything come out in a certain way, and I can come up with an equation that defines the amount of air entrainment. Okay? Now, if you look at this then, so what happens is that, for example, here I took a cylinder. So what happens if I put the fire in the corner?
You change the air entrainment because you couple the surface of.
Yes. So instead of having 2 pi r u rho h, what do I have? I'm going to have pi r halves. Is that okay? So the moment that I do that, I've cut the entrainment by 1/4. So if I look at this equation, then my entrainment coefficient will not be 0.2, but it will be 0.05. Is that okay? I mean, is that clear? So these are empirical coefficients that effectively are being created as a function of experiments, but the logic is pretty clear. So I can actually make corrections to my entrainment correlation in a way such that I take into account things like changes in area. So for example, if I'm going to be looking at the entrainment of a spill plume coming out from a window, then effectively I have only half the cylinder. So instead of having 2, I will have 1, and probably my entrainment coefficient will actually be 0.1. It happened to be, instead of 0.1, 0.089. Okay? Because you're obviously deforming the flow a little bit. But you can see how you can play with the entrainment coefficient as a function of understanding how the scaling was done. Now, if you take all the steps and do the scaling correctly with every detail and carrying all the CPs everywhere you want, eventually you get exactly this term here. Okay? That's exactly what you will get. You will get that term there, and you will get Q to the 1/3 and H to the 5/3. Okay? Now, obviously, as you're changing the geometry, you will get a different value of the entrainment constant. Is that okay? So now that I have MA, then the problem becomes very straightforward. Okay? I don't have to now do much to be able to solve these equations, because effectively I take my change in control volume as I did, okay? And then my conservation of energy as I did, okay? And I get the whole set of equations that I need to solve. So what are the equations that you need to solve? The ideal gas law converts itself into the hot density is equal to the ambient density multiplied by the ratio of temperatures, okay? Then you get your fire is Q is equal to alpha T squared. Then you get your temperature of the smoke layer, that is going to be the ambient temperature plus Q over MA over CP. MA is your entrainment coefficient. I discretize my conservation of mass for the control volume at the top of the smoke layer. So basically this is just a discretized version of it, okay? And then I discretize my conservation of energy, and here is the discretized version of that, okay? And as a function of that, I can go to an Excel spreadsheet, and here is an example, and you can actually construct the whole answer, okay? So I put all these equations in here, and with a simple Excel spreadsheet, I start at time 0, 5, 10, I put a delta T of 5 seconds, okay? Then my next column is my alpha T squared, so I have the heat release rate as it is increasing, okay? And then effectively I can calculate the height. The original height is the height of the compartment, so my initial value is going to be 2.75, which is the height of the room, okay? Then with the height of the room, the heat release rate, and all the constants, I can calculate the entrainment. Rate is actually 0 in the first step. Is that clear? So then once I have the mass of air entrained, I can calculate the temperature of the smoke, because I know MA, I know CP, I know Q, I know TA, but for my first step, I have 0 over 0. So instead of doing that, I just put the ambient temperature, okay? Then once I do conservation of mass in the control volume, which is the mass of the control volume in the previous step, which was 0, times the new mass of air entrainment times the delta T, which is 0. So the new mass at the first step is still going to be 0 because there's no heat release rate and there's no mass, okay? And my temperature of the smoke layer is still going to be ambient because I have not put anything into the smoke layer. So then my new density still is the density of air, okay? And my new height, because I added nothing, the change in height is still 0. Is that okay? Now for the next step, it's pretty straightforward because now I do have a heat release rate, okay? I subtract 0 to the previous one, so now I still have the same height, okay? Because it was the original height minus 0. But now I do have a finite MA, because this is different to 0, this is different to 0, and this is my constant, so I can calculate a mass. Now I can plug it in and get a new temperature. Now with the new temperature, I can actually calculate the mass of the control volume, and I can keep going and again and again and again. Then you copied it, pasted it down, and you can look into how the smoke layer descends. Is that okay? Once you have that, you can plot it, and you can see that the smoke layer starts at 2.75 and it starts descending until it basically hits 0, which is the point where you get to flash over. And the temperature is pretty much ambient for a very long period of time, and then eventually it takes off. Is that okay? Now obviously, when I get close to the surface, my entrainment correlation doesn't work anymore, because it was not designed to have a smoke layer right on top of it, so the whole thing breaks apart. And this very simplistic approach of two control volumes that are exchanging mass and energy doesn't work anymore. So if at the end the height goes to 0, then the mass of air entrainment goes to 0, and the temperature will go to infinity. Okay, so it's going to break down. Now, normally, we consider that by the time you get to about 600 degrees Celsius, the smoke layer will be sufficiently hot to bring you to flashover. So normally what we do is by the time to get to 600 degrees Celsius, which is about 900 Kelvin, you know, we will truncate the solution and say that's the point of flashover. Is that okay? Yep.
Do we need to consider the flame height interacting with some of the upper layer?
Yeah, of course. I mean, I think what ends up happening is that the solution becomes incorrect much earlier than that. So clearly, at some point around here, the flame is going to start interacting with the smoke layer, and the flame opens up, because you get the hot gases pushing the flame down, and the flame cannot push itself through the smoke layer, so you get a flame that opens up, which effectively reduces entrainment even further. So somewhere around here, all this thing is going to break down. Okay? And all these things have to be considered. Now, people have been studying this in detail. Some people have done intermediate smoke layers. So you have a hot, a medium, and a cold, and they've improved this. But the framework is so simplistic in nature that I'm of the opinion that there's really no need to correct. It's much more of an engineering decision of saying, when do I stop? Okay? So what am I going to call flashover? If I'm confident that the solution ends up here at 80 seconds, I can call flashover here. My error bar will be 20 seconds, but who cares? I'm going conservative. So I rather have a simple solution with none of these corrections than start correcting and correcting and correcting, you know, and then kind of lose track of how these corrections are affecting the solution. Is that okay? But that's a decision that obviously an engineer, you know, will have to make on the basis of what they're trying to achieve. But given that what we're trying to achieve is purely being able to compare this time to flashover with the egress time, then this particular solution becomes good enough. Okay? So as you can see, it's a pretty simple and straightforward approach that is based on very basic principles, you know, of fluid mechanics, where in reality, we are just simply doing an energy balance, a mass balance, and doing a little bit of a trick of fluid mechanics to come up with an empirical correlation for the air entrainment. We combine that with experiments, and that way we have circumvented completely the problem of having to numerically solve the entrainment function, you know, on a pool fire. Is that okay? Now, obviously, the range of validity of this kind of things is quite limited, no? Because if you have something that is not burning in the floor under the conditions that you are more or less establishing of your experiments, then everything starts changing in a slightly different way. So nowadays, if you look into, for example, NIST has a code that is called CFAST that has basically modeled all this, is CFAST. Okay? That code will have a library of entrainment functions. So if your fire is in a bookshelf, you shall use this equation. If your fire is in the floor, you shall use this. So people have run experiments with a number of different solutions, and you have a whole library of entrainment functions, okay? Because that's what you're depending from, okay? So in summary, basically, I have a very simple zone model that has two layers, and I'm exchanging mass of air between the cold and the hot layer. So it's only two zones, and that's about it. It provides the evolution of the height and temperature of the hot layer. It obviously depends on the precision of the entrainment correlation, and basically is a result of a simple mass and energy balance between two control volumes, and it's going to break down when the smoke layer gets too close to the surface. When does that happen? It depends on many variables, and you just simply have to make a decision where you stop trusting the analysis. Is that okay? Okay, so I'm going to stop here, and we'll pick it up tomorrow.